Chapter 6 is dealing with random variables. So first of all, what is a random variable? A random variable simply is a variable that takes on a numerical value that describes as an outcome from a chance process. We've worked with random variables already this year, but sometimes the outcome of a chance process could be categorical, other times it's numerical. So if it's numerical, then we can denote it as a random variable and denote it as with a variable letter. The probability distribution of a random variable gives its possible values and the probabilities. We called these probability models before. If it's a random variable, we can call it a probability distribution. Random phenomenon. Roll a die and observe the side that is showing up. If we record the face that is showing, whether the face is showing an even or an odd, is this a random variable? Well, the sample space would be even or odd, because that's what we're recording. These are not numerical variables, so no, that's not a random variable. If we record the number displayed, the number that's showing up, is that a random variable? Well, yes, it would be. Outcomes would be 1, 2, 3, 4, 5, or 6. This is a random variable because it's numerical. Let x equal the face showing up from part B. Find the probability distribution for x. This is also called the probability model. So recall, a probability distribution is a list of the possible outcomes and their associated probabilities. So let's let x equal the face showing up. I don't have to write that down. It's already defined. So let's list the outcomes and their associated probabilities. Outcomes are 1, 2, 3, 4, 5, and 6. Now you could argue that we don't really know the probabilities, right? Didn't say that it was a fair die. If we assume it's a fair die, these would all be 1/6. They should say it's a fair die. We shouldn't assume that. Like I said, we've seen these before. It's just now these x's are going to be numerical, and we're going to be able to do a little bit more with them in this chapter than we did in the last chapter. Discrete random variable. If the numerical outcomes are countable, for example, this would be discrete. You can list them, you can count them. Then we call it discrete. If it's infinite, continuous, we call it a continuous random variable. Oftentimes measures that have a continuous nature, we study them or record them as a discrete random variable. For example, heights of humans are continuous. You could measure, if you had an accurate enough measuring device, you could measure it with infinite amount of accuracy in theory. However, whenever we record it, we really just usually, maybe you're 61 inches tall or 59 inches tall or 72 inches tall. We record them as a discrete random variable. So sometimes there's a little bit of a gray area between discrete and continuous. How many languages? Imagine selecting a United States high school student at random. Let's define the random variable x to be the number of languages spoken by this randomly selected student. The table below gives a probability distribution based on I think in the notes I took off that word sample, based on all of the students from a database. I don't want to take a sample. I want let's say or pretend that this is a probability distribution for all the people in some population of interest. Can languages be considered a random variable? Well, I don't know what languages are, but if we're talking about the number of languages, then yes. The number of languages is a random variable. Explain. It is it. Don't use pronouns. Languages are numerical. So it's a random variable. I don't know. It's kind of a stupid question. Sorry. Is this a legitimate probability distribution? Well, for this to be a legitimate probability distribution, we need to make sure that all of the possibilities are accounted for. For example, is there anybody that speaks 6 languages or 7 languages? To find that out, I guess we would add up all these probabilities and see if they add up to 1. I'm not going to do it. I think if you add them up, they do add up to 1. So we'll say yes. Probabilities, sum to 1.00 or 100%. So it's legit. Make a histogram of the number of languages. Okay, just do this by hand. Outcomes range from 1, 2, 3, 4, 5, up to 5. We'll go to 6. These would be the associated probabilities. Looks like the probabilities go up to about 60%, so I'll call this 60%, 30%. Histogram of number of languages. And this is going to be number of languages. Notice we got a title, label in the x-axis, label in the y-axis, standard fare. So nobody speaks 0 languages, so that's not going to really show up. It just would be 0. 63% speak 1 language. So this bin is going to include the left endpoint and not the right endpoint. 29%, whatever. 6%, ooh, that's small. Then 0.8% and 0.2% are barely even visible on the chart. So that'd be the histogram. It's a little bit different than what we've done before, because before we'd always talk about, we'd count the number of data points in a data set. This is just giving us the probability, so we just plot the probability. Find the probability that x is greater than or equal to 3 given that x is greater than 1. Interpret the meaning of this value. So this is a conditional probability. I'm going to use a formula. This is a probability that x is greater than or equal to 3 and x is greater than 1 over the probability that x is greater than 1. Now recall that formula is on your formula sheet. You don't have to memorize it, but you need to know how to use it. So what is the probability that x is greater than or equal to 3 and greater than 1? Well, as long as it's greater than or equal to 3, it's going to be greater than 1. So this just simplifies to the probability that x is greater than or equal to 3 or the probability x is greater than 1. So greater than or equal to 3, greater than or equal to, that would be these added together. 0.065, 0.08, 0.008, 0.002. And I could break this down. We could talk about this is a probability, x greater than or equal to 3 is a probability that x equals 3 or 4 or 5. Ors are the addition rule. And 3, 4, and 5 are mutually exclusive. You can't know 3 languages and know exactly 4 languages. So we just add them up. Probability that x is greater than or equal to 1, that would be, or not greater than or equal to, but just greater than, that would be all of those. Basically, 1 minus the 0.63. So let's type that in our calculator. 065, 008, 02. 065, 008, 002, 1 minus 0.63, 203%, or 0.20, I can't even talk, 0.203, 20% chance. Interpret what this value means. I don't leave a lot of room, sorry. It means this is a probability that a randomly selected person that speaks more than 1 language speaks 3 or more languages. So 20% of the people, I don't really want to write it down. I'm getting kind of lazy here, but I will write it down. The probability that a randomly selected US kid that speaks 2 or more languages if we're going to interpret the 20%, we should actually use the 20%. I'm sorry. We should say there is a 20% chance that a randomly selected United States kid that speaks 2 or more languages will speak 3 or more. It sounds kind of silly, but given that somebody speaks 2 or more languages, there's a 20% chance that they speak 3 or more languages, which basically means that 80% of them speak 2 languages exactly, whatever.